Up to now, it's very important to understand that the traction over elements, when we have something like this, the traction we obtain over elements, it is in, when we apply traction, it is in ton or kilonewton per meter square. Why meter square? Because it is the total force. We have to multiply by this line, the value of this line, times the one inside the screen. So if this one is 1 meter and this one is 1 meter, so the total force here is the 1 ton per meter square times 1 meter length times another meter inside the screen, so you get 1 ton. All traction here should be applied over the element. So the value here you will get at any node. The value you will get at any node. For example, the value at this node for the element, it should look like this one as a shape function. It is distributed traction like this one. This one is the one that will break it down into triangle and parabola. Triangle in this direction, for example, and the parabola in this direction. Okay, because they should be subtracted from each other. And this distribution in ton per meter square. So when you multiply it by the length of the element times the length of the 1 meter inside the screen, you will get up total force here 1 or something ton, or total force ton or kilonewton or something like this, or pound or anything. This is very, very important. This is very important. When you compute stresses here, sigma 1, 1, sigma 1, 2, sigma 2, 2, or something like that, you will get them in terms of ton per meter square. Okay? And the stress here at this point, it is a distribution. So it has no meaning. It has no meaning. For example, if the stress here is sigma 1, 1 is equal, for example, is 1.2 ton per meter square, that means the stresses here is 1.2 tensile stresses. At this point is 1.2 in this direction. Okay? And we should look at the distribution of the stresses here. For example, we see the distribution of the stresses something like this. Okay? So we integrate, if we integrate the stresses over this area, if we integrate the stresses, we integrate over this section, for example, if we integrate over this section, over this section to the stresses sigma 1, 1, it should be equal to the 1, to the total force here. Okay? It should be equal to the total force from the equilibrium also. Okay, this is very important to understand what are the values, how to interpret these values in terms of reactions. Okay, when we carry out equilibrium, if we carry out equilibrium in sigma x equal sigma the forces in x direction equal 0 or sigma the forces in y direction equal 0, we should carry out equilibrium of forces. We should, this is very important to be written, we should carry out equilibrium checks in terms of forces, not tractions nor stresses. This is very important. This is very important. Why you are doing this? In order to check the results of our computer program. This is for two-dimensional elasticity, but for plate in bending. So plates in bending. So in plates in bending, I'm going to give you a program, a small program. I put it on the drive. You can try it for quadratic element, and you have two types of quadratic elements: continuous element and discontinuous element. Okay, so we will demonstrate our problem here. This problem is very simple, cantilever program. This is plan, so you are looking from the above, for example. So you have distributed load -1 ton per meter square over this area, and you have 3 free sides, and you have fixed sides from here. I'm going to discretize this one using this is x1 direction and this is x2 direction, and this is my origin, and we have 4 elements, 4 continuous elements with these nodes. These are the extreme points. So we have 4 extreme points, and we have 8 nodes, okay, and we have 4 elements. It is 4 meter by 4 meter. Let us see how to write the input file we have. This is the input file. I put the first 2 lines of the input file is for title, okay. You will have it on the drive, all of this. This is the 10 Gauss point for the integration points. This is 0.2 for the thickness of the plate. This is the Young's modulus of the plate. This one is the Young's modulus, and this is Poisson ratio. I usually put Poisson ratio equal to 0 in order to allow me to compare my result to beam theory. And this is the distributed load over the domain area. It is -1 ton per meter square or kilonewton per meter square. Here I'm defining that I have 4 extreme points. These are the x and y, the x1 and x2, 4 extreme points. For example, the first one is this point, 4 and 4, and this is the second point, and this is the third point, 0 and 0 here, and this is the fourth point. And here is the x and y for the nodes. I have 8 nodes. This is x and y for the first node, the second node, and so on. This is x and y for nodes. Okay? Then we will have 4 elements. We have 4 elements, and the first element we have 1, 2, 3, the nodes, the first node, second node, the third node. The second one is we have 3, 4, 5, 3, 4, 5. That means we have continuous elements. Because of that, when I put this one, xi1 and xi2, that means I have continuous elements. The idea here, it is hidden here, is very simple. Here, xi at the middle, it is always 0 at the middle. Xi or eta or something like that. And here, this is 1, and this is -1. Sorry, -1. I'm sorry. And here is -1. So when the point here at 1, that means that I have this one is at 1. And when we have my node here, that means I have at -1. So in the discontinuous element, I can put here at 0.7 and this one at -0.7 or something like that. We'll see in a while. Okay? And be careful. As far as you put your nodes here at 1 and -1, this should be compatible with the coordinate of the nodes. Okay? So you have to be, this has to be compatible with each other. Okay? And these are the extreme points of the elements. The elements extreme points. This is the element extreme points. Okay? For example, the first element between the extreme point number 1 and number 2. And the second one is from number 2 and number 3. And the third one from number 3 and number 4. And so on. Okay? The last one in between the 4 and 1. Okay? And we have 4 lines here. 1, 2, 3, 4. This is called the boundary conditions. Okay? This is very, very important to understand. Let us understand first how can we write these boundary conditions. The boundary conditions, each line is for each element. So this one is one element. So this element we have 3 nodes. At each node, we have 3 displacements or 3 tractions. So the first node, we have 3, 1 is U1. If you remember, U1 like this, and U2 like this. This is U1, and this is U2, and U3 is vertical like this, as plate bending. So in the direction 1, which one is prescribed and which one is unknown? If the displacement is prescribed, we put this value as 0, the value here. Okay, this one for U1, this one for U2, this one for U3. If the traction is prescribed, we put the value is 1. We use this one by the name code by K, is not by C, because we wrote this program in Fortran, and Fortran usually treat this K as integer value. Okay, so if it is 0, that means displacement prescribed, and this one is the traction is prescribed.